This one-week experiment is divided into two parts. The first part deals with observations of metals that are immersed in salt solutions and writing a balanced redox equation for those reactions that do occur. The second part involves the construction of several galvanic cells, with a copper electrode immersed in a copper sulfate solution used as the reference half cell in each galvanic cell. Cell potentials are recorded for each constructed galvanic cell, and ultimately an activity series is constructed from the recorded potentials. The three traditional categories of chemical reactions are precipitation, acid-base, and redox. Precipitates characterize precipitation reactions, with formation of a salt and water typical of an acid-base reaction. Redox reactions involve the transfer of electrons from one reactant to another. Galvanic cells utilize redox reactions and convert the chemical energy resulting from this transfer of electrons into electrical energy. Two processes, called oxidation and reduction, occur when electrons are transferred from one reactant to another. In the reaction between tin and copper ions, the tin is oxidized, since it loses 2 electrons in going from metallic tin to the tin plus 2 ion, and the copper plus 2 ion is reduced by accepting 2 electrons in forming metallic copper. At standard temperature and pressure, these two processes occur in tandem. If something is oxidized, something else must be reduced. This electron transfer may occur either directly or indirectly, and this experiment involves both. The initial test tube reactions involve direct electron transfer, since both reactants are in direct contact with each other. No useful work can be obtained from direct electron transfer. Galvanic cells harness indirect electron transfer, since the oxidation component in a redox reaction is separated from the reduction component by a physical barrier. This arrangement also allows us to measure the potential generated by the galvanic cell. The galvanic cell in this experiment uses a pair of T-tubes that are connected by Tygon tubing but separated by a plastic semi-permeable membrane that prevents the solutions in each of the T-tubes from mixing, but still allows the migration of ions between the two solutions. Each T-tube contains a solution of the oxidized form of the metal that is immersed in it. In the galvanic cell shown here, a copper metal rod is immersed in a salt solution containing copper plus 2 ions, and the other T-tube contains a tin metal rod immersed in tin plus 2 ions. Each of these T-tubes is called a half cell, with both half cells comprising the galvanic cell. The circuit is completed by connecting the black and red wire conductors to a meter that completes the electrical circuit and allows the voltage of this cell to be measured. For the galvanic cells used in this experiment, the copper electrode with copper plus 2 ion solution will always be one half cell, with the other half cell containing a different metal immersed in an appropriate salt solution. Either a conventional electrician's multimeter or a pH meter set to read voltage will be used to measure the potential in volts of each galvanic cell. The red and black conductors are connected to the metals in the galvanic cell by alligator clips. The potential of each galvanic cell is defined as the difference between the reduction half-cell potential and the oxidation half-cell potential. Since the copper plus 2 ion half-cell is used in every galvanic cell, the cell potential you measure in a galvanic cell indicates the tendency of the other half cell to reduce copper plus 2 ion to copper metal. The standard symbolic representation for a galvanic cell uses a vertical line to separate the different phases that are present in a galvanic cell. If a cell potential is measured at standard conditions, then the measured potential is referred to as E0 of the cell. This means all cell pressures are 1 atmosphere, all solution concentrations are 1 molar, and the temperature is 25 degrees Celsius. If the measured potential is not at standard conditions, which is typical for a lab experiment, then the more general cell potential, E cell, is determined by correcting E0 of the cell by subtracting a factor including several constants, such as 2.303, R, and F, and corrects for the actual temperature T and the factor Q, which is the non-equilibrium ion concentrations in both half cells. This equation is called the Nernst equation. The cell potential is a measure of the driving force of the redox reaction occurring in the cell and can be equated to the free energy of the cell by knowing the number of electrons N being transferred in the reaction and F, which is Faraday's constant. Note that the greater the measured potential E, the more negative is delta G, and the more useful work that can be obtained from this redox reaction. The activity series ranks the metals in order of those that are most easily oxidized, in other words, give up their electrons, to those most difficult to oxidize, or hold on to their electrons. Since the copper reaction is the reference half cell in all the galvanic cells, all measured voltages using different metals in the other half cell are relative to copper. Your observations in the test tube reactions give an indication of spontaneity with respect to delta G. That is, either the reaction occurs or it doesn't. The relative ease with which different metals lose their electrons is determined by comparing the measured potentials of the galvanic cells. This comparison will then allow you to rank them in the activity series. The experiment is completed in pairs. When connecting the cell to the meter, the red meter probe is always attached to the copper electrode and the black probe to the other metal electrode. All 0.1 molar solutions have been prepared. You should sand the metals before using them to ensure exposure of pure metal to the salt of its aqueous ions, and the solid metal should be returned since they are very expensive. Standard safety precautions include goggles, lab apron, and closed-toe shoes.